So once you know the wave function for the ground state, you can get the wave functions corresponding to the excited state 1, 2, 3, etc. by using the raising operator. I already told that already if you are in the ground state, there is no point in using that A minus operator because you do not have any energy levels available below the ground state. So even if you operate that A minus operator on psi naught, you will get 0. That's what we found. Okay. So what did we have? We had something like this. The function, and I said this is the ground state, R is some constant and exponential minus m omega divided by 2 h cross R, right? And this ground state wave function corresponds to a energy spectrum En as n plus half h cross omega. This is 3 by 2. This is r square, yes, exactly. And this n can take any integral values. Okay, n has the components of nx, ny, and nz. Okay, this is the capital N. I have already the information about the small nx, small ny, and small nz along the independent coordinates. Independent in the sense individual coordinates. Okay. Now, if this is the ground state wave function along a direction which is r, that means you have this coordinate system, and I assumed a particle like this connected with the spring, and I assumed this as a harmonic oscillator with some amplitude r in 3 dimensions. So I can resolve that. So you already know that I can resolve these r into x, y, z coordinates. So this is my x, and this is my y, and correspondingly this will become z. Okay, z, x, and y. So this harmonic oscillator along a random or arbitrary r direction has an angle theta with respect to z axis, and can have, you can define any angle phi, for example, along the x axis. So that means if you consider the harmonic oscillator in 3 dimension, you should consider its component along x, y, and z. And fortunately, we could resolve these components of potential well or potential values along x, y, z direction independently. And also kinetic energy operator, we could write it in x, y, z components. Okay. Now what you can do is, actually you have the position operator, x operator for example, and the momentum operator. So these are my fundamental operators to explain the dynamics of a system. If I have the position, if I have the momentum, even in classical physics also we could explain everything, every part of the dynamics of the system. How did we define? We knew that you had the position and this was a function of time. So that means dx by dt gave you the velocity. This is classical mechanics. Dx by dt gave you velocity, and if you multiplied that with the mass, you got the momentum, and you differentiate this again, you will get the d square x by dt square. This gave you acceleration, and again if you multiply it by m, you get mass times acceleration, which is force. And once you have the force, you know how to get the potential. Okay, force is negative gradient of the potential. So just by knowing these x and p, for example, you know exactly how this behaves, how this particle behaves. Similarly, if you can replace this position by the position operator and the momentum by momentum operator, you should be able to explain everything about this system. Okay, this position operator and the momentum operator can actually combine together in various forms. Okay, one way these people or these guys combine is by having something like this. X cross Px. That's like a cross product of the position and momentum. Or in general, in three dimension, I can write this x in terms of r cross p. This you know from bachelor's. What is r cross p? It's angular momentum. Okay, so that means if you know exactly the position operator and also the momentum operator, remember I'm talking the three-dimensional object here. You can reduce this to one single dimension by using x and px, for example. But in general, I have a system which is in three dimensions. So obviously, I need to consider the r, the position vector, plus the momentum in the three dimension. Okay, and if you find this r cross p, what you get is the angular momentum. Okay, this is also an operator because you are having the cross product of two fundamental operators. So that means I can use this operator and I can operate this operator on this function. I get some value. This is what you do. You have an operator, you operate that on the wave function, and you get some value, which we call it as eigenvalue. Okay, so operator operating on the wave function gives you a value and a function again. Okay, and we call this as eigenvalue equation, or yeah, eigenvalue equation. And this function is a special function provided it gives you a value. It is called eigenfunction, and the value you got was eigenvalue. So that means if at all you create an operator L using the fundamental operators position and momentum, that means this operator should also act on the wave function and it should give you some value. Okay, we'll try to find out what is this value. Now remember, your problem is not simply x and px. You're not finding the cross product between the one-dimensional position and momentum along one particular direction. You're actually finding out the cross product in three dimensions. So that means this r should have the xyz component. This p also should have xyz component. So equivalently, you can write this as something like x, y, and z. These are position operators, and you're finding out the cross product between these position operators and px, py, and pz. If you do this, then you should get correspondingly the angular momentum information. Okay, we'll try to find out what does this give you. If you operate, or if you find a cross product between the position operator and the angular momentum operator, sorry, the linear momentum operator, you will get the information over the angular momentum. Okay, once you start writing like this, it already tells you something about this wave function. Okay, just try out this one. R cross, what is P? P operator is the first derivative with respect to whatever coordinates you have. So in general, in three dimension, I can write this as minus IH cross del by del R, dou by dou R. Okay, the first derivative with respect to this position coordinate. Okay, what is the first derivative of? So what we do is we operate this operator on the function. So that means you're actually doing L psi. L psi is whatever this operator on psi. Okay, so R cross minus IH cross del by del R on psi. This is what you're going to find out. So what does this tell you? The first order differential of the function with respect to the position coordinate. What does this tell you physically? What is the first order differential mean? Vi, so di by dv, what do you get? That's the first order differential, right? V by I gives you the resistance, or I by V gives you the conductance. So this also tells you how the current changes with respect to the potential or voltage. So similarly here also, the first order differential of the function with respect to r is the position vector in 3 dimension, and I have assigned a ground state wave function just like this. And if I find the first order differential of that function with respect to r, I will get the information about the angular momentum of this. Okay, so it already tells you the rate. So the L actually implies the rate of change of the function, wave function. I will write psi in any direction r. That's the first order differential, right? So angular momentum need not be something specially defined. It is just the way in which the function actually changes with respect to r. Okay, or you can also write this as any in radial directions or direction r. So once you define this ground state function, this is for a 3-dimensional harmonic oscillator. So that means if I can find out the first order differential of that function in 3 dimension, so I exactly know what is its angular momentum. Of course, that this formula should be there, r cross IH cross del by del r. Okay, is it okay? Yeah. Now, if you know this function, remember we do not know what is the mass, we do not know what is the position, etc., etc. What I know is just the wave function of this particle. So if this has a 3-dimensional motion, from the wave function I assign, I know exactly what is the angular momentum. Okay. Now, what about the kinetic energy of this? If this is in 3 dimension, what is the kinetic energy? You just know only the wave function. You already know that the kinetic energy operator is minus h bar square divided by 2m del square by del x square. So the second order differential of the function with respect to x gave you the kinetic energy information. Just like that, in 3 dimension, you can write minus h bar square divided by 2m del square by del r square. This will give you the kinetic energy information of this particle, which is actually free to move in 3 dimensions by knowing only the wave function, remember. Okay. So that means it is imperative to know what is this L correspond to. We should know this L in some detail. Okay. Once you know L, that means the rate of change of this function in 3 dimension, for example, that corresponds to the particle momentum, angular momentum. If you find the second order differential of this function, that corresponds to the kinetic energy of this. Okay, you just try to apply this first order differential with respect to r. What will you find? What I mean is, this L is r cross p, right? So p is minus IH cross del by del r. So you just find out L psi naught is what? Just use this function. Psi naught r is given by this one. Just find out the first order differential and find out what you get for L. So this will be r cross minus IH cross the first order differential of this function with respect to r. What do you get? This is A times e bar minus m omega divided by 2h cross r square multiplied by m omega divided by 2h cross times 2r. Is it correct? Minus. Okay, fine. No problem. You can add minus. What do you have effectively? Effectively, you have r cross r. Okay? This is m omega h cross. All these are constants. So r cross some constant times r cross r is 0. That means angular momentum for a particle in the ground state for a symmetric potential. Remember, we assign this wave function for a symmetric, three-dimensionally symmetric potential. We get angular momentum 0. This is just by using this r cross p relation, where p is written as the first order differential with respect to the position coordinates along 3 dimensions, and I know exactly this wave function in terms of r coordinate. Okay, and I substitute that, so you get L0. So there is a very famous statement about this one. What is that? Oops, I don't have. Okay, please write down a spherically symmetric wave function. A spherically symmetric wave function psi of r corresponds to a state. Remember, this function corresponds to a state which is given by E naught as half h cross omega. So spherically symmetric wave function psi r corresponds to a state with 0 angular momentum. Okay, so L becomes 0. So if at all you can define the particle with a spherically symmetric wave function, that already tells you that the angular momentum is 0. Okay. Okay, so let's go slightly deeper into this angular momentum concept. As I said, this is in 3 dimensions, so that means it should have a x component, y component, and z component, Lx, Ly, and Lz. So if you were to do a measurement of an angular momentum experiment, for example, can you determine its x component, y component, and z component together? Okay, I'll tell you, go to the lab, measure the angular momentum, and the system is in 3 dimensions. So that means the question will be, can you determine the Lx, the angular momentum component along x, Ly, and Lz simultaneously? The logic says there is no problem of measuring x and y component when you measure the angular momentum. But in fact, nature does not allow you to do that. Okay? You either can measure Lx, you will never have any information about Ly and Lz. You can either measure Ly, no information about Lx and Lz. How to prove that mathematically? I want to measure this Lx, Ly, and Lz simultaneously. Yes. So the statement we learned a few lectures back says that uncertainty principle and then the commutator relation. Okay. So what should be the commutator relation? Let's say Lx and Ly. Okay. I want to find out what is Lx, Ly commutator relation corresponds to. I want to find out what is Ly and Lz corresponds to. I want to find out Lz, Lx corresponds to. If this commutator relation are 0, then you can simultaneously measure this. Lx, Ly, if at all it is 0, that means you can measure this simultaneously. If at all Ly and Lz commutator relation is 0, you can measure it simultaneously. Okay? So that means our job today is to find out these relations. That's what my experiment is. I want to find out the angular momentum, and since it is in a three-dimensional object, obviously it will have x, y, and z component. Now, if you go and do the experiment, do you get all these components together at the same time? Okay, we'll try to find out. So the angular momentum already you know is given by r cross p. Okay, so you just write L as r cross p. Let's go back to mathematics and we will try to find out what exactly this gives you. This is xyz, this is px, py, and pz you have. Okay, I can write this as I, j, k, and x, y, and z, and px, py, and pz. If you find out that, then you will get the x component, y component, and z component. Okay, so let's write down. This will be a little bit tedious, but that will spice up our lecture. You know, you need mathematics to spice up. Okay, so what is this? I times ypz minus zpy plus j. You can write minus, you can write plus. Okay, so I'll write plus, no confusion. Okay, plus j z px minus xpz plus k times xpy minus ypx. While you already know x and p has the commutator relation I h cross. That means you cannot determine the position and momentum simultaneously. Remember, this situation is always existing. So remember here, ypz, that means y and z, z and p. That's the momentum again. And similarly, z and x, x and z, x and y, y and x. Okay? So you can write this as, in fact, I, maybe this is the x component of the angular momentum, because this is what I'm trying to find out. Okay? Plus j times Ly plus k times Lz. So what do you have? Lx is y pz minus zpy, Ly as zpx minus xpz, Lz as xpy minus ypx. Okay, these are the relation of the component of the angular momentum along three perpendicular directions. What you need to know if you want to find out the x, this commutator relation you need to know. If you need to know the y component, this commutator relation. Okay, you can expand this in fact. So what is Lx? Ypz minus zpy. This gives you y. What is pz as an operator? It is minus ih cross dou z. Okay, minus z times, again py will be minus ih cross del by del y. This is what you have to find out. What you are going to get is actually a function like this, and if you operate that on with the Lx, you will get the value, the x component of the angular moment by this operation. Okay, or you can write this as minus ih cross, because it's a common factor. I'll take this out, y times del by del z minus z times del by del y. So this is my Lx. you operate this function, so you will have to find the first order differential with respect to z. You'll have to find out the first order differential with respect to y and solve that. Okay. So similarly, you can write this one. What is Ly? Okay, let's do it. Instead of just copying it, let's do this y component, Ly. Okay. So Ly is zpx minus xpz. Is it correct? Yes. So this will give me z times minus I h cross del by del x minus x times minus I h cross del by del z. So that means Ly. So this corresponds to minus I h cross y del by del z minus z del by del y. Similarly, this will be minus I h cross, that is z by del x minus x del by del z, and this will be correspondingly I h cross. This is z. Remember the relation. It's very, very simple to remember. So x, y, and z. It is just a cyclic operation. If you want to know the Lx, for example, the only terms which are contributing are z and y. You see here y and z, z and y. If you want to know the Ly, the contribution is from z and x. So that means if you want to know Lz, the contribution is from x and y. Okay. So this will be x times del by del y minus y times del by del x. Okay. So these cyclic operations are always available in physics. Remember that. And remember the direction along which it goes. If you want to have z, it's the clockwise rotation. Remember, you cannot write y and x because these are operators. So the direction along which you operate matters a lot. Okay. So that is my Lx, Ly, and Lz. So now the problem is not solved. My question was whether I can measure Lx, Ly, and Lz simultaneously. Okay. That means I want to find out what happens to Lx, Ly operator or commutator relation. What happens to Ly and Lz, for example, or Lz and Lx. Okay, let's try to find out Lx and Ly commutator relation, and the sequence is similar to Ly and Lz and Lz and Lx. Okay. So the job is to find whether I can measure this simultaneously. Remember, we are not doing mathematics just because we know how to do mathematics. We are trying to find out in an experiment whether I can measure the angular momentum components simultaneously. That's the question. Okay. You might have any system, any harmonic oscillator, for example, in three-dimensional defined. So whether the question is, can you determine its x and y and z component of the angular momentum together simultaneously? Okay. The way in which you determine is to find out the commutator relation, and you find this becomes 0. If that becomes 0, that means you can simultaneously measure. If it is not, then you cannot. Okay. So let's try to find out what is Lx and Ly. Lx, Ly. What is this? This will be Lx, Ly minus Ly, Lx. Okay, let's do it. Lx is, you can use this way or you can also do this way. Let's use this one. Okay, so this will be y pz minus z py. This is Lx. And what is Ly? Zpx minus xpz. This is the first one, Lx and Ly, minus Ly is Zpx minus xpz times this one, ypz minus zpy. Remember, every component here, every term is an operator. So the way in which you put this product matters a lot for the relation. Okay, so you cannot just randomly pz and y. You cannot do that because that relation is completely different. Okay, so what is next? So just find the product here, y pz and g px. So this is done. So please stop me if I go wrong somewhere. Y pz times x pz, that is this one, okay, and minus z py z px, and this is plus z py and x pz. Okay, so I'll just write this one minus now this one z px y pz minus z px z py minus x pz y pz plus x pz g py. Okay, oops, yeah, that's correct. There are few terms which I'll cancel out. Okay, what remains is only minus IH cross LZ. That means it is Z. So XPY minus YPX. Okay, and this will be minus IH cross. This is LZ. Is it correct? Just the problem with the sign. Oh yes, it is plus. So this is plus IH cross LZ. Okay. Remember, you can write, you can combine this one, and so PZ and Z and Z and PZ. So you can write, combine these two. There are two terms cancelling out. The only what remains is IH cross XPY minus this YPX. Okay. So that means LX Ly commutator relation will give you IH cross LZ. Similarly, Ly LZ will give you IH cross Lx, and Lz and Lx, the commutator relation, is IH cross Ly. So obviously it tells you that it is not zero. So that means you will never be able to get the value of Lx, Ly and Lz simultaneously. You have to do separate measurements. Okay. So this term cancels out. This is minus G. G is an operator. It is just a multiplication. So you can multiply on the left or right. It is same. So G and G, Py and Px. This is Px and Py. So it is actually cancelling out because it is positive here. Okay. This will and this will match. And please solve this and you arrive at this relation. This is plus. Okay. So simple formation of this commutator relation directly tells you about the experiment you can do. How about magnitude of the angular momentum? How do we find the magnitude of the angular momentum? There is an operator which is called L square operator. Just like in the case of vectors also, the magnitude of x and y, for example, in 2 dimension is found by x square plus y square. Similarly, you have L square operator, which will give you Lx square plus Ly square and Lz square. This is an operator that gives you the total angular momentum, magnitude of the total angular momentum. Okay, and it's written as Lx square, Ly square, and Lz square. So this is the magnitude, and these are the components. So that means if you go and do the experiment, what will you find? Whether you are able to find L, that's the magnitude of the angular momentum, and let's say Lx, whether you will be able to find. Whether you will be able to find the magnitude of the angular momentum and let's say Ly. Again, use the same commutator relation. Okay, use the commutator relation between L and Lx. If you get 0, then you can measure it. That means if you can design your experiment in such a way that you want to measure the x component plus the magnitude of the angular momentum, you can do it, provided that commutator relation gives you 0. Similarly, you can design your experiment to measure the magnitude plus Ly, one of the component. You already know that you cannot get 3 components together. So that means at least one of the components should be available for measurement. If one of the component of the angular momentum plus the magnitude of the angular momentum in 3 dimension, to see whether you can measure it, you also have to find out what is the commutator relation of L square and let's say Lx. I want to find out the magnitude and the x component of the angular momentum. Okay, Lx, that's the component along x-axis, and this is the total magnitude of angular momentum in 3 dimension. So I want to find out. So that means you have to find out the commutator relation between L square and Lx, and you find out whether it gives you 0. If it gives you 0, yes, you can measure it. That means just by one experiment to find the magnitude of the angular momentum, it already gives you the x component, or similarly y component, for example, or at least one of the component along the perpendicular directions. Okay, so you can write this one as Lx square plus Ly square plus Lz square and Lx. Correct? L square is the magnitude of this angular momentum vector in 3 dimension. This is vector addition. X square plus y square will give you that dimension of the vector in 2 dimension. Similarly, along the 3rd dimension also you can add. Okay. Now, Lx and Lx is 0. What does this mean? These two are same. So that means it is equivalent to saying that you can measure simultaneously Lx. So it is 0. So that means you do not need to consider when you want to find out this commutator relation, right? So effectively what you have is Ly square plus Lz square Lx is my job to find out the commutator relation between this sum and the Lx, and we have to find out. Okay. One of the classic experiment of finding out the angular momentum, one type of angular momentum was historic, which is called the Stern and Gerlach experiment. But there is a difference. What I'm talking about is L, not S. Remember, okay? There will be a lot of experiments. I will tell you what experiments you can do to determine angular moment. Okay. The problem is we cannot do it in our labs. We cannot determine these things. Okay. How about this one? This is actually equal to Ly square and Lx plus Lg square and Lx. The commutator relation between the sum plus and the Lx will be the individual term and individual term. Okay. Ly square can be written as Ly times Ly. Okay. So this will be Ly times Ly Lx plus Ly and Lx Ly plus this one Lg comma Lx plus Lg Lx and Lg. Is it correct? Yes. Yeah. Okay. So I just erased the commutator relation between these two, and these two, and these two. Please tell me what is Lx and Ly. Ly is minus I h cross Lg plus. Remember this plus. And Ly Lg is plus I h cross Lx. And what about this one? Lz Lx is plus I h cross Ly. Who will substitute these things there? If you give me a non-zero value, then you'll get some prize. Lx Ly operator commutator relation is plus IH cross, means Ly Lx will become minus. Okay, so you can write it as Lx Ly minus Ly Lx. Ly and Lx commutator relation will be Ly Lx minus that one. So you just have to take one minus sign. Okay, write it clearly so that everybody understands. Is it correct? Okay, what do you get? Okay, all cancel out. Everybody agree? Okay, so write 0. Okay, so this means that L square and Lx operators commute. That means L and Lx can be simultaneously measured. Okay, while Lx, Ly and Lz cannot be measured simultaneously. Okay, so that means in any experiment, you cannot just intend to do the experiment in such a way that I want to know Lx, Ly, and Lg only, because the experiment will not give you that. What you have to do is you measure the magnitude of the angular momentum, then it allows you to find out one of the component of the angular momentum also, whether it's x, y, and z. You can find out what happens to L square and Ly. This will also become 0. Similarly, L square and Lz also become 0. So these four operators, okay, L square, Lx, Ly, and Lz, these four operators are very, very important in terms of experiments, because just by the commutator relation, you know that they cannot be simultaneously measured, x, y, z components. The other way around is I measure the magnitude of that, and then it gives me an option to find out x or y or z component. Okay, that's the meaning of this. So what did we learn today? We said if at all it is spherically symmetric, wave function, then L is 0. This is one message. If at all you have a state, energy state or quantum state, which is defined with a spherically symmetric wave function, then its angular momentum is 0. That means the magnitude of angular momentum is same in every direction. Okay, and Lx, Ly, and Lz cannot be measured. Cannot be measured simultaneously. Okay. The third point is, to avoid this complication, what I do is I measure the magnitude. So that means L and Lx or Lx or Ly or Lz can be measured. Okay. So now you should tell me what actually it is in terms of a diagram. I'm just drawing you. Okay, drawing here. So I have a system here. Let's say uh, some particle here, and it is at a distance of r, and it is actually, imagine this is in 3 dimension. Oops. So I hope this is a circle. Okay. Okay. And you know that this is mv, this momentum, which is p. P cross r gives you the angular momentum. Okay. So that means your angular momentum vector is perpendicular to this plane L. So this particle here, which classically can be defined as m and moving with certain velocity, angular velocity also possible. So you can define a momentum, and it is at a distance of r because it is in 3 dimension. Okay. So if you know these two parameters, you can immediately tell me that the L is perpendicular to this r and p, because L is r cross p. This cross product immediately tells you that it is perpendicular vector. Now L directly tells you how the function assigned to this particle actually changing with respect to r, changing with respect to the angle. Okay, if at all this particle is in the ground state, psi naught r for example, then it directly tells me that it is spherically symmetric. Okay, if at all it is spherically symmetric, then I know that L is equal to 0. The angular momentum is 0.